Hello, can you see my screen?
Hello, yes.
And you also can hear me, okay?
Yes.
Okay. Can I start with the presentation? Please give me an input when I should start.
In the chat, there are some informations, I guess.
Okay.
¿No lo hago aquí? En este. Tú me vas diciendo los que están online y los que no por el WhatsApp, ¿vale? Hello, Rudolf.
Hello?
Hello, perfect. Are you connected?
Yes, I have to share the screen.
Yes.
Yes, can you see the screen?
Yes. Perfect.
This is first presentation.
Well, we start the next session of the Congress with the communication with the title High Energy Efficiency Electrical Drive with Multi-Level Inverter and Wide Bandgap Power Semiconductors by the University of Applied Science. Can you start, please?
Yes. Good morning, everyone.
Good morning, everyone.
The title of my presentation is High Energy Efficient Electrical Drive with multi-level inverter and wide bandgap power semiconductors.
Let me start with
a motivation for this work. Multi-level inverters are established for high voltage applications.
The new idea is
Let's extend the application to the lower voltage range. That means between 560 and 750 volts. And the aim should
improvement of
the improvement of the efficiency by using new wide bandgap switches. Moreover, multi-level inverter could have further advantages. For instance, smaller motor filters
and
inverter size, lower voltage transients at the motor windings, and so on. So and the most popular
topology is
this neutral point clamped 3-level inverter,
and it can be
equipped with 600 volt
with
switches
lower conduction
and switching losses compared to the commonly known 1200 volt devices.
So the calculation of
the conduction and switching losses is described in detail,
this
and this diagram shows the results.
it compares
It compares the 2 and 3-level inverters with IGBTs and wide bandgap MOSFETs at 150 degree junction temperature.
So the wide band
materials
achieve an extreme
reduction in switching losses,
and the lowest losses
on the
occur
on the 2-level inverter with silicon carbide MOSFET. This is a light blue curve. However, further advantages of the multi-level inverters would be lost in this case.
So for a higher
number of inverter levels, a simulation model is developed,
and the bridge legs
for 4 or 5 and 7 inverters are shown in this slide.
The
blocking voltage of the switches
is reduced
with a number of levels. For instance,
for the
5-level inverter, we
a
need
blocking voltage of
300 volts.
So the simulation
of the conduction and switching losses was done with the best power switches on the market,
and you can see
this
chosen
switches between
this blocking voltages
between 1200 and 100 volts.
So the simulation
model of the switches is integrated into these
complete model of the drive system,
and
the complete model consists of the multi-level
inverter, the motor filter,
and
the motor cable, and
motor
the
itself.
induction motor itself.
So and the conduction and switching losses
for different inverter levels are shown for an 11 kV induction motor at 100 degree junction temperature.
So the wide bandgap
switches have a clear advantage over IGBTs, and the greatest loss reduction of 60% at nominal motor operation point
is achieved with a
with a 2-level inverter by replacing
IGBTs
with silicon carbide FETs. This is a light blue curve.
So and with a 5-level
inverter, a further reduction of about 10% is possible.
This can you see in this
magenta
but
curve.
The 7-level inverter
increases the losses,
so that the 5-level
inverter
is an optimum in this
configuration.
So
at this slide, you can see the classification of the losses.
These are the conduction losses
of the FETs. This curve. Then the conduction losses of the freewheeling diodes
and the conduction losses
of the clamping diodes.
You can see the
conduction losses of the clamping diodes are predominant. That means
for improvement of efficiency,
these diodes have to be in the first step.
So this slide
contains the output voltage
of the 2-level,
the 7-level,
and the 7-level
inverter at 10 kHz switching frequency.
And as you can see,
with a number of levels, the output voltage
the
sinusoidal shape,
and the harmonic
content decreases.
As a result, the natural frequency of the motor filter
which reduces the size of the filter, of course.
So this slide shows the volume and weight of the motor filter for various inverter levels
And switching frequencies,
and by increasing
the number of levels from 2
to 5
to 5,
and the switching frequency
from 4 to
40 kilohertz.
40 kilohertz.
Volume and weight can
Volume
be
and weight
reduced by
can be
about
reduced by
80%.
about 80%.
But a further increase in the number of levels and the switching frequency
does not result
in any further
reduction of volume and weight.
This is right.
Shows the correspondent power losses of the motor filter,
and the losses can be
reduced by about
65%.
65%.
And with a 7-level
inverter and 50 kilohertz switching frequency,
a small additional
reduction is possible.
So the slide
shows the inverter and the filter losses in one diagram
as a function of the motor
A
power.
considerable reduction is already achieved
with a 2-level inverter
by replacing IGBTs with silicon carbide MOSFETs. You can see this light blue
Another
reduction is achieved
by the 5-level inverter
with 40 kilohertz switching frequency.
magenta
Curve,
but the
7-level inverter increases the losses again.
So
Overall,
by using 5-level
inverter, the losses at nominal motor operation point are reduced
from the state of the art by
60% compared
to the 2-level inverter
with IGBT. This is a slight green curve. This is state of the art at the moment.
So the diagram shows the efficiency of the motor
as a function of motor power
and at nominal
motor operation point.
At nominal motor operation
point, the 2-level inverter with
silicon
silicon carbide FETs
can improve the efficiency
by about
2%.
2%.
This is a
light blue curve
to the light
compared to the light green curve. The improvement is about 2%. 2%.
So and the 5-level
inverter with 40 kilohertz switching frequency achieves an efficiency of more than 98%.
So and this is
an improvement of 2.7%
compared to the
state of the art.
With a summary,
I want to finish my presentation.
Multi-level inverters
could be an alternative for industrial drives.
I think the
right time is now because new wideband gap switches are available.
The first step is the replacing of IGBTs with silicon carbide FETs in the 2-level inverter
and further loss reduction of a 5-level inverter can be achieved with GaN FETs. An additional reduction of the motor filter by about 80% can be achieved.
But the higher complexity and investment costs
for multi-level inverters are the great question.
Thank you, Rudolf. If someone has any question
this was
for
the end.
this
Thank you for your attention. Thank you for your attention.
someone online wants to make any question. Well, Rudolf, I have a question. If you can put your presentation slide number 15, please.
Yes, number.
Okay.
So, yes, can you see the screen?
Wait a moment. I think it's in the efficiency of 3L. There is a big difference between the other two. What do you think is this difference? I want to show you in the slide.
Please repeat the question. I have. Okay. Please, can you repeat the question?
Lebanon. In this presentation, I will be discussing how our proposed three-phase transformer-less inverter is able to totally eliminate the common mode noise in photovoltaic grid-connected system. In the 21st century, the PV source becomes one of the propitious ways for power generation since it's not polluting, efficient, and climate-friendly. This idea is strengthened in this graph that shows the evolution of the annual global PV market in megawatt. As illustrated, the global market of PV systems is increasing continuously over the years. In specific, Lebanon significantly struggles in its electric power sector due to the power mismatch over the years between the production and demand. Unfortunately, since the power plants of Electricité du Liban are not able to assure a continuous supply of electricity, private diesel generators are used to cover the shortage in power generations. So in order to enhance its power generation and decrease the emissions of polluted gas, the country promised to profit from environmentally friendly sources such as PV. In the same context, a study was made to show the most reliable PV farms locations as shown in this map. Also, Lebanon can benefit from the wide range of PV applications and try to implement, for example, the grid-connected PV systems, which can provide a solution to overcome the shortage in power generation. In this type of systems, inverters are used as a connection point between the PV source and the grid. They are capable of converting the DC signal coming from the PV panels into an AC signal entering the grid side. Grid-connected PV inverters are divided into two categories: inverters with galvanic isolation and inverters without isolation. The galvanic isolation is provided by the transformer. However, these isolation transformers are massive, difficult to implement, and add extra losses to the system, which cause the overall efficiency to decrease. So in order to overcome these complications, transformers are eliminated. This fact will not only reduce the complexity of the system, but also decrease the cost and increase the efficiency. However, the absence of galvanic isolation causes a generation of common mode leakage current. To elaborate, this image shows a general model of a transformer-less PV inverter system where the leakage current flows through the parasitic capacitance of the PV panel. This undesirable common mode noise can add losses to the system, cause electromagnetic interference, increase the output harmonics, and lead to safety problems. For the purpose of evaluating the leakage current issue, it is important to differentiate the concepts of common mode to differential mode. So given any circuit, the common mode voltage is defined as the average of the voltages from each output terminal to a common reference. For the system shown here, N is taken as the common reference. Thus, the inverter common mode voltage is given as follows. The differential mode voltage represents the voltage across the output terminals of the inverter, and it's characterized by the following equation. Now, based on the differential mode voltage, we can derive the additional common mode voltage. Consequently, in the equivalent common mode circuit, the total common mode voltage is obtained by adding these two voltages. This total common mode voltage must be constant without variation in order to suppress the leakage current. Therefore, researchers were encouraged to promote helpful transformer-less inverter topology to achieve this goal. In single-phase system, some of the topologies failed in lowering the leakage current level, and the rest succeeded in reducing it to acceptable levels. Two of these topologies, the virtual DC and the multi-level half-bridge, were able to completely eliminate the leakage current. The multi-level half-bridge topology overcame the problems faced in the virtual DC-based one. Therefore, it can be an excellent selection for a single-phase system. As for the three-phase systems, some of the topologies failed and the others succeeded in lowering the level of this common mode current to acceptable levels. However, to the best of our knowledge, none of these topologies was able to completely remove the leakage current. Therefore, the aim of this work is to find an inverter structure that can completely eliminate the leakage current in a three-phase system. This is achieved by extending the single-phase multi-level half-bridge topology to a three-phase system. The proposed topology is characterized by a simple inverter structure, can totally eliminate the leakage current, it's able to generate multi-level output, and is based on a simple modulation technique. This is the selected single-phase topology where we have three-level inverter, and it can be modified to operate at a higher level output. This inverter consists of two parts, switch 1, 2, and capacitor C1 forming the first half bridge, switch 3, 4, and capacitor 2 forming the second half bridge. Let's discover now how by implementing this topology we can totally remove the leakage current. Referring to this previous circuit, it can be graphically proved that by directly connecting the PV negative terminal to the neutral point of the grid, the stray capacitance will be bypassed, leading to a zero leakage current. We can also prove this theoretically by showing that the total common mode voltage is cancelled. In this topology, the inverter has an asymmetrical inductor distribution where L2 is equal to 0, leading to a null voltage at terminal 2. Consequently, the following equations are obtained. Thus, the leakage current is totally eliminated since no variations will occur in this zero total common mode voltage. This three-level inverter topology can work in two modes, 1 and 2. In mode 1, C2 is charged to half of the value of the DC input voltage. This leads to a three-level output, VDC over 2 minus VDC over 2 and 0. However, in this mode, the inverter acts as a half-bridge inverter, so it requires an input DC voltage which is the double of that across C2. In mode 2, C2 is charged to the same value of the input DC voltage, leading to a three-level output VDC, 0, and minus VDC. However, in this case, C2 is not naturally balanced. To solve this issue, we can see that there exist two switching states that lead to a zero output voltage. In the first zero state, S1 and S4 are turned on to charge the capacitor C2. In the second zero state, S2 and S3 are turned on to conserve the net charge of the bypass capacitor C2. In this way, the capacitor becomes balanced. Let's look now at the system elements. Using MATLAB Simulink software, a Trina solar PV array is used. So in order to work correctly, it must be fed by two inputs, the irradiance and the temperature. Here we have the proposed three-phase inverter, where three single-phase inverters of the desired topology are connected to each other, and the negative terminal of the PV panel is directly connected to the neutral point of the Y-connected AC grid voltages. The module capacitance is obtained using this derived formula, and the grid voltages are operating at a frequency of 50 Hz with a voltage equal to 120 volt. In the inverter controller, a maximum power point tracker is used based on the incremental conductance technique. The control is based on the synchronous reference frame concept, where Park transformation is utilized in addition to a proportional integral controller with the following transfer function. A phase-locked loop block and a DC voltage regulator block are added to the inverter controller. The control strategy of the inverter differs between mode 1 and 2. In the first mode, the control of the inverter is very simple since the voltage across capacitor C2 is naturally balanced. The conventional sine pulse width modulation technique is utilized in mode 1, and its output is used to generate the appropriate switching gate pulses for the inverter. In the second mode, the control strategy is modified in order to maintain the voltage across capacitor C2, which is not naturally balanced. The control strategy used in mode 2 is illustrated in this image, where the flow diagram is applied to generate the appropriate switching gate pulses for the inverter. In order to check the validity of the proposed topology, the three-phase inverter is simulated in both mode 1 and 2. In mode 1, the PV array generates 400 volt, and the capacitor C2 is charged to half of it, 200 volt. The plots of the output voltage and the voltage across capacitor C2 are shown here, V0 in blue, VC2 in orange. When the PV array generates 400 volt, C2 charges to approximately half of it, 200 volt. This leads to a three-level output voltage varying between VDC over 2, 200 volt, 0, and minus VDC over 2, which is minus 200 volt. Same for phase B and phase C. The three-phase output voltages are delayed by 120 degrees to each other, leading to a balanced output. Also, the inverter of this PV system is operating at a unity power factor, where the grid current is in phase with the output voltage. Same for phase B and phase C. In mode 2, the PV array generates only 200 volt now, and C2 is charged to the same value of it, which is 200 volt. This leads to a three-level output voltage varying between VDC 200 volt, 0, and minus VDC minus 200 volt. Similarly to mode 1, the inverter is also operating at a unity power factor. Same goes for phase A and phase C. To sum up, this proposed multi-level three-phase inverter can be considered as a promising topology in three-phase application, since it showed satisfactory performance. This proposed topology has simple inverter structure. It can completely remove the leakage current in a three-phase.
Question about this communication, please. Well, Katya, there is no question in the room. Just can you tell us which is the next step of the research, if you have thought about?
Hello everyone, can you hear me?
Katya?
Hello everyone. Yes, are you hearing me?
Have you hear us?
Yes, can you hear me? Okay, so as future work, we are looking to study the efficiency of this topology by studying the losses in terms of conduction losses and switching losses. Also, we need to further validate the functionality of this topology by trying to implement this topology on hardware in order to compare the results with the simulation.
Okay, thanks. Well, we
Many
start
thanks.
with the next communication. Is in the room. Well, in a minute, start Professor Luis Sainz from the Department of Electrical Engineering of Polytechnic University of Catalonia, Spain.
Okay, I am Professor Luis Sainz from the Department of Electrical Engineering of the Universidad Politécnica de Catalunya of Spain. And I'm going to present the paper Frequency Domain Stability Assessment of Photovoltaic Power Generation Systems with Quasi-Zeta Source Inverter. The schedule of the presentation is the following. First, I introduce the problem. After that, I present the model of the studied system. Once we know the model of this system, I talk about the stability assessment of the quasi-zeta source PV power systems. After that, I present a short example about the study, and I finish the presentation with the conclusions. Renewables of PV systems are replacing fossil fuels in power grids, and these PV systems have single or two-stage designs. The single-stage configuration based on Z-source inverters, such as quasi-zeta source inverters, are becoming an attractive alternative due to it offers different advantages in front of the other configurations. However, PV systems are formed with power electronics, and these power electronics often cause a risk of instabilities in the systems. In order to study these instabilities, there are different approaches. The most known approaches are the state space eigenvalue analysis and the frequency domain methods. Nevertheless, there are few studies which deal with the quasi-zeta source in PV power generation system stability. Most of them only focus in the assessment of the converter stability, and there are only a few studies on dynamics of the complete system. In this benchmark, the contributions of the paper are the following. The paper presents an S-domain model of the quasi-zeta source PV systems derived from the small signal state space average equations. Once we know the model, or we have the model of the system, the paper also presents an approach for system stability assessment, and this approach is based on the frequency domain characteristics of the state space matrix determinant. Minor contributions of the paper are the study of the impact of the system operating point on stability and the validation of the stability approach by the eigenvalue analysis and PSCAD simulations. The studied system is presented in the slide. On the left, we have the PV plant, which is connected to the AC grid on the right by means of the quasi-zeta source inverter. And moreover, we have the controls of the system at the bottom. On the left side, the bottom, the left side, we have the control of the maximum power point, the PV panel voltage, and the current controls of the converter. And at the bottom, on the right, we have the control of the duty cycle of the quasi-zeta source converter, which imposes the value of the DC voltage at the terminal of the voltage source converter. First of all, we must model, we must write the state space equations of each module of this system. We start with the state space equations of the PV panel, which comes from the linearization of the PV panel around the maximum power point. And we have the linearized circuit of the PV panel and the corresponding state space equations. The other equations corresponds to the, at the top, the state space equations of the grid, and at the bottom, the state space equations of the controls of the maximum power point, the PV panel voltage, and the current controls. The last are the state space equations of the converter and the control of the duty cycle of this converter at the bottom of the slides. All of these state space equations are linked into the general expression of the state space equation system. These state space equation systems can be reorganized in order to obtain the transfer function Fs of the system, which relates the inputs of the system in order to obtain the outputs of the system. Note that this transfer function depends on, at the bottom, of the determinant of the state space matrix. Once we know the model, the state space equation model of our system, we can start the study of the stability of the system. This stability study can be made from or by means of two approaches, the eigenvalue analysis and the frequency domain stability criteria. Regards to the eigenvalue analysis, it's known that we must obtain the eigenvalues of the state space matrix, and if the real part of these eigenvalues is negative, that means that the eigenvalues are in the right-hand plane of the eigenvalues, the system is unstable, and the frequency of the oscillations of this unstable system corresponds to the imaginary part of these eigenvalues. With respect to the frequency domain stability criterion, I'm going to present this stability criterion based on the determinant of the state space matrix. From the transfer function of the system, we know that this transfer function depends on the determinant of the state space, and for study the stability by means of this transfer function, we must analyze the poles of this transfer function. That means the zeros of the determinant of the state space equations. To analyze the zeros of the determinant, we can use the method proposed in reference 13 in the paper, which can be applied if the real part of the eigenvalues is smaller than the imaginary part. This method states the following. The zero crossing frequency of the imaginary part of the determinant provides the frequency mode of the eigenvalues. At this frequency, we can determine the real part of the determinant and the slope of the imaginary part. And if the product of this real part and the slope is negative, we can assert that the system is unstable. This method is applied in an example where it is studied a PV panel which delivers 1 kilovolt and 140 kilowatts to a strong 400 volts AC grid. The data of the system is presented in the table. First, how can I go back? with the arrows. Yes. We are going to study, I'm going to study 4 operating points. The first one is the stable and the reference operating point, where it is delivered power from the DC to the AC grid of 66 kilowatts with a DC voltage of 790 volts. The second and the third operating point corresponds to an increase of the active power delivered to the AC grid until 80 kilowatts and 94 kilowatts. And the unstable point will be the 94 kilowatts. And the last operating point corresponds to the fourth, where the DC voltage is increased until 990 volts at the operating point of active power 94 kilowatts. First, we study the stability by the eigenvalue analysis. In the slide, we can see the plots of these eigenvalues. On the left, the eigenvalues for the operating point 1, the reference, where we have all the eigenvalues, and we can see that all of them are in the left-hand plane, so the system is stable. On the left, we have only the sum of the eigenvalue related to instability. And we can see the evolution of this eigenvalue when the parameters of the operating point are changed. For example, we can see the evolution from operating point 1 to operating point 2 and operating point 3 when the active power is increased. And we can see how the eigenvalue crosses the zero line and goes to the right-hand plane. So the operating point 3 is unstable. And the frequency of this unstable point corresponds to 150 Hz, the imaginary part of the eigenvalues. In order to recover the stability of the system, we can increase the DC voltage, and then we go to the operating point 3 until the operating point 4, going back to the left-hand plane, okay, which corresponds to the increase of the DC voltage. So we can note that the increase of the active power delivered to the AC grid leads to system instability. And on the other hand, the DC peak voltage increase allows system stability to be obtained again. This study, the stability study, is also performed by using the proposed frequency domain method based on the determinant of the state space matrix. For this, we can plot on the right and the top the imaginary part of this determinant, and at the bottom the real part of this determinant. First of all, we must locate the crossing points of the imaginary part. And we can see that these crossing points characterize the frequency of the oscillatory modes at 150 Hz. Once we know which is the crossing point of this imaginary part, we can determine the value of the slope of the imaginary part. You can note that the slope of the imaginary parts, all of them are positives, and the value at the bottom of the real part. We can see that all real parts are positive, but the third point, the third operating point real part is negative. So the product of the real part by the imaginary part of the third operating point is negative, and at this operating point the system is unstable. Last, we can verify the results obtained by the eigenvalue analysis and the frequency domain criterion proposed in the paper by means of PSCAD simulations. We have the evolution of all the operating points and the response of the system. We can see on the right that for the first operating point at 66 kilowatts and 790 volts, the system is stable. And now we increase the irradiance level at the PV panels. We increase the active power delivery to AC grid. First to operating point 2, the system remains also stable. And after that to third operating point, increasing the power to 94 kilowatts, keeping constant the DC voltage. at this third operating point, you can observe that the system becomes unstable. And the frequency of these oscillations is just the 150 Hz, which is predicted by the studied stability methods. In order to recover the stability, in the fourth operating point, we increase the DC voltage until 990 volts, and the system again goes back and returns to the stability situation, as the stability criterions predict. As conclusions, the paper presents a small signal state space average model of the quasi-zeta source inverter PV power generation systems. From these models, the paper assesses the stability of these systems by means of the frequency domain stability criterion of the determinant of the state space matrix. And the influence of the operating point on stability is studied. And we can note that the increase of the active power delivered from the DC to the AC side can provoke system instability. The increase of the DC voltage reduces the impact of the effect of the active power on stability. And all of these results were validated by the J-value analysis and PSCAD simulations. Thank you for your attention. If you have any questions.
Thanks, Professor Luis Sanz. Someone wants to make any questions? I think it's clear. Many thanks.
Okay.
Well, the next...
Thank you very much.
Can you fix it?
Yeah. Okay, thank you.
Okay, thanks. Well, continuing with this oral presentation, next contribution is continuous cross-period single-phase shift control for dual-active bridge converters by Mr. Skaboitz. No.
Yes. Can you hear me? Can you hear me? Can you hear me? Yes. Okay. So and probably see me as well. So just a minute. Okay. My name is Szabolcs Vereb, and I'm a PhD student at the University of Budapest University of Technologies and Economics and the Department of Automation and Applied Informatics. And today I want to talk about a new control method for dual-active bridge converters, which is called the continuous cross-period single-phase shift control. First of all, what is the motivation behind this paper? Basically, is that we have a modular hybrid drive system laboratory at our university. There's a picture of it. So you have various motors here, and you can use those to test motors or use them as a driving or loading. And also you can test various parts of hybrid drivetrains of air vehicles. And you can also test inverters and even batteries because we have multiple kinds of power converters behind those cabinet doors. And one of them is actually an isolated bidirectional DC to DC converter, which is built around the dual-active topology. It has a 360 kilowatt nominal power, and its purpose is to keep the voltage balance between its output and input, and it must have a good, very good low transient response because we are a test laboratory, so there could be various things happening with the current levels. So where is this DC converter? DC converter is actually here behind these motors. I I want to talk a little bit more about how you can control a DOP converter and why the most common single phase shift control is not good for our application. And then I will introduce in a very nutshell a control which is maybe applicable, but it turns out it's not. And after that I will explain a little bit more the new control which is inside the paper, and then I will show some test results and comparison to the traditional control. That will happen in the next 10
So first of all, the DOP converter is basically a transformer, two full bridges connected to the primary and the secondary side.
So nothing too complicated.
In reality, in our laboratory, it looks
on
like
the left image, you can see the primary
on the left
side,
image, you can see the
two
primary
half
side,
bridges,
two half bridges, and the capacitor banks with some boost bars and water cooling. You can see very similar things for the secondary side on the right image.
More capacitors,
a little bit more capacitors, and in the middle, behind those contactors, which can be used to select different
turns ratios.
transformer turns ratios. There is the transformer, and here is the control card, which has a DSP inside, which can control the bridges through optical cables.
So how you can control the power flow of a DOP converter?
The idea is that you provide a square bridges, a square wave or a square signal onto the primary side of the transformer on the secondary side. And if you provide two square waves between these two square waves, then there will be a voltage pulse during this time on the transformer, leakage inductance of the transformer, which allows you to change the current which is flowing through the leakage inductance, so what is flowing through from the primary to the secondary side, or on the either direction as well.
And of course, if the
voltages on the primary and secondary side are very similar or nearly equal, then the current won't change too much when no phase shift happens. So this is the basic idea of the single phase shift control, which is the most commonly used. What is the problem with this? Actually, DOP converters are usually used with high frequency switching frequency to keep the size and cost low. But the problem is in our application that the power level is quite high, and it's very hard to build up this kind of transformer core from ferrite material. So we decided to keep the cost low, to use a 400 Hertz laminated steel core transformer. Results with very low switching frequency, and thus with this control method a very slow reaction to changes. We would have overcurrent problems and very bad load regulation.
To solve this problem, we have
created a new kind of control method which we published earlier.
Basic idea with this control is to subdivide phases into 6 phases, one switching period of the original single phase shift control. We kept these phase shift values which are in the phase 4 and phase 1, between these two
switching actions,
we can do various things to change the current without changing
transformer without changing the magnetizing
current. So this way the transformer sees 400 Hertz basically, but actually our control can run 3 times faster. So what we can do is by switching we can create a very inverter voltage across the transformer leakage inductance, or we can short one side of the transformer for a short time. Then it will create a lower pulse voltage. So we have multiple options to choose from. What is the problem with this?
Actually, the control loop uses a forward feed for this control inside for this control.
That is not good if you have
an LC circuit on the output of your converter, which turns out in our laboratory is
the cable inductance and various capacitance of other inverters. So this creates basically a very bad oscillation. So this is not a good approach. To mitigate this issue, we have came out with this new control, which is our paper is talking about. This is basically a slight improvement CPSPS control. CPSPS control. The basic idea is similar. We short the transformer between regular SPS so we can change events. So we can change the trajectory of the current. But this time, we continuously doing this. I mean, if we don't want to change the current, then even we short both sides of the transformer for a fixed amount of time. But if we want to change the current, we just short the transformer one side for a different amount of time, so we can create a current change as well. The advantage of this is that the dead time problems can be mitigated easier, and also now the controller can continuously run, so we can do switching actions even there is no load transients. So for this control loop can be used. So we will have a voltage control which tries to keep the voltage difference between the secondary and primary side at a defined level. We will feed this error value which will give out the transformer current inductance or leakage inductance current value which the controller wants to see on the transformer. We measure back that value, and based on this difference, we can calculate how much phase shift do we need. So we will have a phase shift value from this, and also if you want to make sure that your transformer core is not saturating. So you can measure back magnetizing current DC component, and you have to have a PI controller for that. So you will have another phase shift value here, and you feed these phase shift values to a modulator, basically a lookup table or something like this. You can figure out which switch when do you want to switch. To tune the PI controller, you have to write up the full control loop transfer functions, and you can see it here. So the PI controller is just a regular PI controller, and the current model basically, as it's a model-based controller, it just has a delay. The plant itself is just a capacitor, basically. But we are charging with the sampling, and also because of the sampling implementation or digital implementation, you will have another delay, and these delays can change if you are using the regular or our SPS control or our new control. So our new control is that's why it's better, because it will have less loop delay. You can tune this controller, and we have done this for Texas Instruments PSP, but we are using it in the laboratory to have the fastest overshoots. You can find out an overshoot. You can find the details how we done that in the paper. How we test it and how we test it to the regular SPS control. In the laboratory, we have an active front end which creates a 675 volt DC voltage itself from the grid itself. Then we connected this voltage to the DOC converter input side, and the output side was connected to another DC to DC converter. This is a regular high power converter, where we can create a load current change for the DOC converter, and we were circulating the power, so the losses were minimal. Test cases we had from 0 amps to 250 amps in 1 millisecond. We had this in the opposite direction, and also a 250 amp DC current with a superimposed sinusoidal waveform to see how to mitigate this disturbing current value. Here are the test results. So on the top you can see the voltage and on the bottom the converter, and on the bottom the current of the DOP converter. On the left side you will see the SPS control, and on the traditional control, and on the right side the new control. And but you can see from 0 amp to 250 amp jump up, that the voltage change is much lower with the new control traditional one, and also traditional one, and also this is true for the 250 to 0 amps. You can see it's much lower. You can see it's much lower, and also voltage change, and also the regulation is much faster. And this is true also for the 10 superimposed AC test. You can see that the amplitude of the AC component of the voltage is much lower. You can see in the display Fourier transform that the amplitudes are much lower, and also the harmonics are lower as well. So this controller is faster in reality, as it should be. So the conclusion is that we have presented a new kind of control for top converters, which should have an improved loop transient response. We presented the control scheme and how you can tune this controller or implement it in a discretized DSP environment. And we tested this in a real application, and concluded that yes, this control has better low transient response than the traditional one. So that was my presentation, and if you have any questions, I'm here to answer them.
Many thanks, sir, for your presentation. My congratulations by your presentation. Very nice laboratory. Here in the room, someone was impressive of big motors in that laboratory you have there. Well, if someone has any question in the room, well, all is clear for us. Well, we are waiting for the next presentation. Design of LLC resonant converter for powering a PEM electrolyzer from the University of Research Council of Italy, Palermo.
Okay, I'm sharing my screen.
Presentation.
Yes.
Mr. Vitale.
Yes. Okay, I hope you can see my start.
Yes, can you start, please?
Thanks. So, this contribution described the design of LLC resonant converter for powering a PEM electrolyzer. So, it's an activity in cooperation with the University of Palermo and the Green Laboratory of University Henri Poincaré of Longwy, France. So the paper addresses the design of LLC resonant converter supply a proton exchange membrane electrolyzer. Electrolyzer requires a low voltage and high current, reduced output voltage ripple, and an overdynamic behavior of the converter, so to avoid the voltage overshoots. And the design aims to compare the advantages and drawbacks of LLC converter for this application and to address specific improvements. So the
Well, the sound is lost. We will try to recover the presentation. Gianpaolo, can you listen us? We are waiting for Gianpaolo. He's trying to connect it again. Well, this is the last presentation of this A3 session, oral session. We will wait 5 minutes. We were waiting for the continuation of the communication design of ILC resonant converter for powering at PEM electrolyzer from Mr. Gian Paolo Vitale, National Research Council of Italy. As it is the last oral presentation, we cannot go on with the next one. He was connected all the morning. Well, as we don't have a video recorded of Mr. Vitale, I think we are going to close this oral presentation and to end this session thanking the local committee for this organization and the chairman, Mr. Professor Manuel Pérez Doncion. Let's go.